Okay, so the first speaker in the afternoon session is the Riccardo Muolo from RIKEN Center in iTHEMS and also Institute of Science Tokyo. And title is Dynamics on Chains and Cochains, a topological approach to synchronization. So please.
Okay, thank you, Ishikawa-san. Thank you to the organizer. So I'm not going to use a microphone. If you cannot hear me from the back, with usually I'm loud enough. Standardly, but this should capture my loud voice. Okay, so yeah, thanks to the organizer. It's a pleasure to be here. Since some of you don't know me, also within iTHEMS, I don't think everybody knows exactly what I do. Will be introducing myself. I have a bit of hybrid background of math, physics, engineering, and so on. But mainly, I'm interested in nonlinear dynamics on higher order networks, which is just a fancy way of calling coupled nonlinear ordinals. So synchronization, in particular the Kuramoto model, I will talk about it today, pattern formation. But mainly, I'm interested between in the interplay between topology and dynamics. So when I talk about topology, so the topology that I'm talking about here is a bit different than this topology, because when we have a network, and as I will show, how the nodes are connected, we talk about topology, which is a bit different than the mathematical definition of topology. So I'm a bit in the edge between math, physics, and control. In iTHEMS, I'm with the biologists, to give an idea of how confusing is a bit my profile. But I define myself as an applied mathematician. Yeah, what I study is coupled nonlinear ODs, and they are coupled via networks. So basically, we consider the systems are interconnected, and network is an abstract representation of many different systems. In particular, what we look is oscillatory systems. So, for example, brain dynamics, or how the heart cells are connected, power grids, and so on. But then network can also model social systems, transportation systems, ecological systems, and so on. Now, one limitation of networks, they are very powerful. Since the early 2000s, they are used a lot in physics, engineering, and also other disciplines, but they have the limitation that they encode only interactions one by one, which are called pairwise interactions. However, in many systems, interactions are not pairwise. They are so-called higher order, or many volume and pairwise. There are different names. But in general, anything that is not just one by one. Main examples come from social science, where peer pressure, group behavior are very important. But also in ecology, for example, where the first species can mediate between the interaction with other groups. And neuroscience. So neurons do not interact in a pairwise way, but they interact with this group behavior, with this group behavior. So what physicists have done, they have extended the concept of network by using mathematical tools that were already available. So hypergraphs, which is a direct generalization of network. So now the nodes are not just connected by links, but they are connected by the so-called hyperedges, so these hyperlinks, or simplified complexes, which are a particular case of hypergraph. And there are some literatures, in particular some reviews, if you are interested in this extension. So what I talked to you about today is one of the side projects that I have. I think it's probably the most interesting for theoretical physicists. That we talked about in this perspective is the so-called topological signals, that are these variables that are not only defined on the nodes of the simplified complex, as in classical dynamics of networks, but are also defined on edges and faces, and also volumes and so on. Okay, so basically they are discrete differential forms. We will get to the definition in a second. And they're called topological signals, mainly by Ginestra. She's our collaborator, and she's one of the main researchers in this field. because we can define these variables due to the topological constraints of these simulation complexes. So that's why for topological simple. But basically are discrete differential forms. So to be able to approach this topic, there are three main ways. The most pragmatic is the engineering way, because they care about more the result. And probably these papers are the clearest. One can also approach it from applied mathematics perspective, especially linear algebra. But then I think the most interesting is the one by genetics and network science, is the one we for. Okay, so just the basics. We have our simplicial complex. We go up to two dimension. So triangles or faces, but everything can be extended to any dimension. It just simpler to represent it. Okay, so we have the nodes, we have the links, and we have the faces. In this case, the triangle. So this is a simplified complex. So this is a simplified complex. So the first thing, you have to choose an orientation. So we take the convention that nodes that are zero-dimensional topological space and no orientation. Okay? Links are one-dimensional spaces, so we take the orientation as positive by convention from the lowest label to the highest label. This is the convention. That the physics doesn't change if you change the coordinate. And then, in the same way, we orient the faces. And so the nodes, links, and triangles are represented in this way, and this is what makes us simplified complex. But the set of zero simplices, one simplices, the links, two simplices, the faces. And simplex, the end of the lengths. So nodes are zero dimensional, zero simplex, links are one simplex, and so on. Now, chain and cochain, so n chain and cochain. So a one chain, for example, is a linear combination of oriented links. Okay? A zero chain is a linear combination of nodes, two chain, and so on. Now the cochains, they are the functions that are defined on the chains. So if we go to classic dynamics of networks where coupled differential equation, they are zero cochain. If we study a function on links, this is a one cochain. And there is a caveat because the physics has to be the same when we change the orientation. So one cochain has to be odd one. So that when you change the orientation, they keep the same, they also follow that. And these are basically discrete differential equations. So now that we have chains and cochains, we can define the boundary operator and the co-boundary operator. So basically, the boundary operator allows you to go one dimension down. So if we have our edge, the boundary are the two nodes. If we have a triangle, the boundary are the three links. Okay, this is why we need a simplicial complex. So I cannot be using this one. So in a practical way, if you have your one chain, by taking the boundary, you go to the zero chain. Okay, and so from the two things, sorry, you take the boundary and you go to the one chain. The co-boundary in this context is the adjoint. So you do the inverse operation. You go one dimension up. While with the boundary, you go one dimension up. And we have the rule that the boundary of a boundary, so the co-boundary of a boundary is zero. So you can only go one dimension up or one dimension down. Two dimension up. Now, basically all these cochains have a discrete vector interpretation. So if we are considering a variable on the nodes, so we are considering a zero cochain, taking the co-boundary of a zero cochain is basically like making a discrete way. Okay? And if you are considering a variable on the links, so on the one chain, we have a one cochain, taking the boundary is basically discrete library. For the variable on the link, taking the tuple boundary is basically the discrete pair. Okay? So here is where the connection with the theoretical physics can be more interesting because Laplace Nixon loops, they cannot be represented in this format. It's not what I do, but I know that they can be interesting in C theory. So now, what I'm interested in is on the dynamics of these cochains. So I'm interested in coupling cochains of different dynamics. Okay, and here Ginestra defined a discrete Dirac operator that is able. So if we have a system that has a variable on the nodes, links, and faces, is able to couple this variable, and it's called Dirac operator, so Dirac-Bianconi operator, because its square is the modular function. And so now we can see the interpretation of vector calculus because the Laplacian is the divergence of the gradient in vector calculus. And also here on networks, on discrete spaces, the Laplacian is exactly the discrete divergence of the discrete gradient. Okay? And so it also gives an interpretation of how particles can diffuse in discrete spaces because if you start, for example, from the nodes, you have to diffuse from node to node, you have to go to the link and then go back to the link. If you are on the links, you can either go to the nodes and then come back to the links, or you can diffuse one dimension up to the faces and then back to the so for studying dynamics, this is quite nice. Okay, now let's see a bit of dynamics. That's what is I'm more interested in. So I could talk about this model for 1 hour, but I don't have this time, so I will just introduce it briefly. So some of you may have heard about Riccardo from Kyoto University. He studied synchronization, so this behavior that is responsible, for example, for our heart rhythm, because we have all the cells that fire on the same line, they are synchronized. He was able to obtain a very simple model describing this emergence of synchronization just by the thing. And this model is very famous because it can be analytically solved. And so basically what Kuramoto-san showed is that if you have a system of coupled oscillators, each one with its own frequency, when you have zero coupling, so you don't have this part, the oscillators are all going with their own basic frequency. So by considering a parameter is called, or the parameter is linked to the center of mass of the phase, they are all oscillating without interacting with each other, so they're all scattered, and the center of mass of the phase is about 0. And then Kuramoto-san, together with me, showed that there is a critical value of the coupling, after which these oscillators start to be locked. So this is a second order transition to synchronization. This is why this model is very important and stuff. Now yeah. Yeah, thermodynamics meaning. Yeah. So the simulations are doing for n very large, not n very large, but yeah, I would say it's yeah. And global coupling, so everyone is interacting. Yeah. So yeah, of course, I cannot introduce it properly, but so it's just a very important model in synchronization expedition methods. One thing I can say about the modular Laplacian that can be important is that so there is a relation between the kernel of the modular Laplacian and the Betti number of the solution complex. Okay, so the nth Betti number of the structural complex is exactly the dimension of the kernel of the modular Laplacian, of the nth modular Laplacian. Okay, so this Kuramoto model can be extended to this framework of chains and cochains, and it was extended by Ginestra called Topological Kuramoto model. That basically it is the extension of the parameter model, but now the phases are not just on the nodes as in the classical parameter model, but now they are cochains. So they can be on nodes, on links, on phases, and so on. And now I'm not really a physicist, but I know that physicists care a lot about Hamiltonians. So actually the topological Kuramoto has an Hamiltonian formulation, and what is very interesting is that if you don't consider the frequency, so you consider omega 0, which you can always transform in the co-rotating system, the ground state, the generality is the n number. So there is again the interplay between topology and dynamics. The topology of the simplicial complex or the set complex gives you the degeneracy of the ground state of the unit. Now I'm more interested in the synchronization properties. So now if we consider a system,
Sorry.
yeah.
So that n of sorry, what is n?
N is the dimension we are considering. So if we are on the nodes, n is equal to 0. If we are on the links, n is equal to 1. So
And anything here or
this is general. This is the
for
general.
so different n define the different order.
Yes. So if we have sorry, n equal 1, we have the class parameter. We recover the parameter. So we have this part. If n equal 2, we are now considering the dynamics of 1 cochain. Considering the selection from the leads, not on the lead.
So for it, so that nothing but the time and
Yeah, exactly. Yeah.
and for two so then can you write the explicit form for example to n equal to
Yeah. Definitely. Can we turn this up?
oh sorry yeah then more space.
Okay. So let's say that we have a system like this, the usual node links and node for base, 1, 2, 3. So we define the orientation induced by the labeling. So from 1 to 2, all 2 to 3, and then 1 to 3. And then the same for the triangle. Okay. So now the boundary operator B1. So now it's let's say now we have n equal 1. So sorry, I made a mistake. N equal 0. We recover the Kuramoto model because this is 1 and this is 0. Then n equal 1. We are on the boundaries. So let's say that now we are considering phi 1, phi 2, phi.
So for one the space is defined on
the links.
B.
Yeah.
Okay.
Not on the nodes. And then phi 1, 3. These are the phases. Okay. Now we want is the boundary, so it goes from links to nodes. Okay, so here we have the nodes, and here we have the links. In this case, it's 3, 3, but it doesn't have to. Okay, so the first link, phi 1, 2, goes from 1 to 2. So we have -1, 1, and 0. Then this goes from 2 to 3. So we have -1 on the tail and 1 on the head. And then this goes from 1 to 3. Okay, this is B1. And then B2. We have one triangle. And we have 3 Ds. Okay, so here are the 3 Ds. And here is the triangle. So this is 3 times 1 matrix. So the triangle is oriented positively with the first two links and negatively with the third. So it's a 1, 1, minus 1. So now we have this system with the three phases. What was your question?
My question was the expression for.
Okay.
Probably by sign of one with that.
Oh, it's taking element-wise the sign. So this is basically is B and plus 1, so in this case B2. This is B2, and then is so this is B2, and then you have the sign of them element-wise. So you have this B. So basically, this is a vector. That is the sign of B to transpose theta. Yes, element 1. First row. And then sign of, say, B2 theta, second row.
Oh, you know,
Yeah. It's a bit of weird notation, but it's the only way to write it in this compound. Okay?
And so if I now define the one for
Points.
I, yeah.
Yeah.
Yeah, I,
Yeah.
1, 2, 3, so they correspond to 10.
Yeah. And what's interesting, and I will show in the next slide, is that not only, so when you are considering a network, so depending how the elements are connected, I don't know, whether like this, it affects the synchronization of the phases. Now, to affect the synchronization of the phases on the links, there is also the phase. And there is a relation between the Betti number and the synchronizability of the cell complex. Okay, I think, yeah. Okay. It's okay for the time because the last part I only put it if I had time. So, okay. So, now, as an example, we took this octagon. So we have this double octagon. So basically, yeah, we have these nodes that are connected by links. The two octagons share a link. And then here we have three cases. In this case, we have phase here, and here it's a hole. So the first Betti number is 1. Okay, this is like the number is homomorphic to the door. So this is homomorphic to quadrant. Then we can have two holes or no holes. And this affects the synchronization. So let's first see the case in which the first Betti number is 2. So there are two holes. I cannot put the screen, but okay. It's time. I am. Okay, so we see that both octagons, the links, are oscillating. The coupling is not too strong, so then they do not synchronize. Say for some moment, they don't have a full synchronization. Okay, so we see that we have this very clear dynamics of the links. Okay, nothing strange. Now, if we cover one phase, that's when things become interesting. Because the phase basically increases the dynamics. It makes it slow down. While the other octagon is oscillating with the same frequency as before. So the presence of the phase, the fact that the topology is different, the Betti numbers are different, it is the dynamics. And because I'm interested in the interplay of topology and dynamics and on the control, This is, I think, very interesting, especially if we consider that this edge variable can model certain nano-oscillators. For example, this is, I don't know the details, but I talked to engineers who are very interested in this framework to model nano-oscillator. And then a magnetic field has another representation in a phase. This gives some possible applications. And now the last, but you can imagine the answer. If now we have no phases, these are the initial conditions, the dynamics is completely flowed. And go back. Yes. Okay, so this is what we see here for the case of Betti number, first Betti number 1. I put in red the links with the phase, and in green the links without the phase, and you see that the dynamics is much, much slower. So we can control the synchronization patterns.
Well,
Yeah.
okay. So for one, phase size for discrete size of one.
For n equal 1, here we have no zero differential.
Oh,
We have the
okay. So five.
n
Equal two. Okay. So n equal.
no. Sorry, n equal 1. N equal 1. Yeah. We have the
Yeah.
one.
About so the discrete size of one.
Yeah.
And that so B is B1 test is a discrete size of two. Right. And that's B is
No. This is again.
so one is a sphere and one is a two form.
They are all 1/4.
That's one. And
Yeah.
so B, well, it's something like the difference B and the B that we start.
Yeah.
So
Yeah.
one test is a discrete size of two.
Yeah. So this is basically the influence
Yeah.
of the phase. So in this term.
So how do you define sign of two?
This is just the sign of the difference. It's element y. It's a weird notation.
Oh,
But here is because then you take again the boundary, so you go back to the one form. You don't have the forms here.
So so we P and we is
Yeah. But then we don't have our class because there is the sign in the middle.
So I'm useful.
I know, but this is just the notation with the same parameter as before. This is the component y. It's not really that before. It's just a trick to be able to write it in a compact form. But basically, yeah. So I think I should have put an explicit example. Yeah. So this is basically the effect. These terms gives you how the forms are affected by the phases. While this term gives you how the one form are affected by the nodes. So basically, this term tells you how the one form interact via the nodes, and this term how they interact via the phase. But yeah, it's really okay. Yeah, thank you. I will do next time. And since my time is up, I was going to talk about topological Turing patterns, but it's okay. I will just conclude by thanking my collaborators with whom I'm still working on this. I've worked and I'm still working on this topological synchronization, and thank you for your attention.
Is there any question and comment?
Yeah. In principle, we can have a very strong interaction via the nodes and a very loose via the, sorry, not the nodes, the n-1 simplicity and a very loose with the n+1. This is the protein list.
So if we set it like that, they have
Yeah. But it's what you expect, right? If here you take this sigma to be, you take sigma 2 to be very low, then you don't see the tree. So the stronger the interaction here and the strong and this the red curve is lower.
So it's not very for one. It's well, yeah. So like this theory. So the variables, the mean variables on the get connection behind them. In that case, there is a very similar. There in this model.
No. So the most interesting thing that I see is when there is no symmetry. I look for implementation pattern.
Something that where it's the pilot of 2 right? So you have to do this. Yeah. Okay, yeah.
Any other question or comment? No? Okay, the time. Okay.
This is just because if you are let's say this is the space in which your dynamics you have one chain is the space where dynamics takes place, and then you are starting the dynamics of the one chain. So to see the interaction via the nodes, okay, you first go one dimension down, but then to be able to come back, you have to use the co-boundary operator. And it's the opposite in this. To see the interaction, how the phases interact via the phases, you need to take the co-boundary operator. But then you want to see the F phase, you want them to interact in the one chain, in the space of the one chain, you have to take it out. I also get confused with boundary to boundary with Cochains chain terms.
Okay. Another question? Okay. Okay, let's thank speaker again.